Microphone on. Alright. So, yes, Kopano, last time, where did we finish off? We finished off at grade 9 geometry, ne? We looked at a line and a line segment, ne? And a line we identified for it has infinitely many points, yeah? Then a line segment is a portion of a line that we can measure from point A to point B. Then that has a definite number of points from point to point, yeah? From where it starts to where it ends, a line segment. Then we identified how we can use a ruler, or rather we learned how we can use a ruler to construct lines, with measuring. Then we discussed angles, looking at the key concepts, vertex, which is the point where the angles form. So if you have two line segments where the one segment ends and the other one starts, that will be a vertex. It's the same as a tipping point or a tip.
No, it doesn't.
Oh, it doesn't show here. Okay. Let me open here. So we'll just use this one. Yeah, so we discussed up to here, ne? Then you just click next. So then we also looked at how we construct angles. We looked at the difference between a protractor and a ruler. So ruler in a linear graduations and protractor in a pizza slice, like very thin pizza slices. Yeah? And you get 360 of those in one revolution, and one of those pizza slices is called a degree. And 1 degree is got a little zero at the top. Ne? All right. Then next slide. We discussed types of angles, starting with acute, meaning sharp, right, meaning so when you click, you use left click, ne? Right click, that will give you these options. If you click with your right finger, it will give you these options. If you click with the left finger, it just clicks. So then we discussed right angle, which is 90-degree angle, and you find this in the corner of your house or room, or table or screen. Then obtuse angle, little bit bigger than a right angle, but not a straight line. And straight line is 180 degrees. So anything that's flat or straight, like this table here, is 180 degrees. Reflex is more than 180 degrees and less than 360 degrees. Then revolution is 360 degrees. Next slide. We also looked at how if we put protractor on an angle to measure it, So this would be a protractor, and these two lines, line 1, line 2, and this would be the angle, Then the reading we get, the reading that we get on the protractor, so in other words, from 0 degrees to X degrees, that will be the angle measure, Okay. Then we continued. So this one was not accurate. Next slide. Although this one was not 100% accurate, it was to show how we would measure an angle using a protractor, 100%. And then we also looked at how to construct, in the next slide, a 90-degree angle. You have a line segment. So where it starts at A, you put a compass, the one end of a compass that has a pin and the other end of the compass that has the pencil. You put it there, you make a arc, small arc there, and then you also do below the line. Then you take the compass to the other end, B, the end with the sharp point, the pin, you stick it at point B, then you draw an arc above the line AB and below the line AB. Now where those four arcs intersect, you join the points and then you have a right angle. Yeah? And then we looked at geometric figures. If we want to draw a circle, we will place the pin of the compass there and then the pencil end at the end. Now that distance gives us a radius. Which is half the diameter of the circle. So diameter would, let me just make it like that. Yeah. So half would be radius, but the full distance would be diameter, né? Which is 2 times radius, né? Yeah. So you must always know this, because when you work out perimeter and area of the circle, you will use, when you calculate perimeter and radius of circle, you'll always use diameter and radius. Né? So area and perimeter of circle, you will always use the information about radius and diameter. Then we looked at different triangles. Right angle triangle. We also looked at isosceles triangle, and that the isosceles triangle will have 2 equal sides and those equal sides, those 2 equal sides, they are next to each other, and the angle between them is different from the 2 angles at the bottom, but the 2 angles at the bottom, they are equal to each other. So like this triangle here, AB equals AC, the angle at B equals the angle at C, but the angle at A is a different size. And then we also did a little bit experiment of making triangles, so that we can see that the sum of angles in a triangle is the same as 180 degrees, which is the same as straight line. Then here, did I give this as homework? But the goal is to say the angle, next slide, the angle outside of a triangle, if you have a straight line extending from a triangle, so the angle outside equals to the sum of these 2. So in other words, the angle DBC equals angle BCA plus angle BAC. So in all these cases, so in all 3 cases, angle DBC equals angle BCA plus angle CAB. Yeah, so in all of these 3 cases, this angle outside equals the sum of these 2 angles inside. And then next slide. Oh yeah, then we discussed geometry. So algebra to accommodate our classmate. So now today's class, we will be looking at, I'll just make this one here. So today's class, we will now look at geometry. So we're carrying on from the last part, Yeah. So read for us.
Bisecting.
Start there.
This technique of constructing 90 degrees angles, 60-degree angles, and bisecting angles allows for the construction of many other angles without using a protractor.
Oh, okay. That's a good trainer. Discussion is about constructing 90-degree angle, which we did, and then 60-degree angle, and then bisecting angle. So 60-degree angle, I'll just make note of why it's important. 60-degree angle is important in an equilateral triangle. Lateral triangle. Then there's a bisector. So bisector is important because it sections or divides an angle into two equal parts. Into two equal parts. So in other words, if we're gonna left 90-degree angle, a 90-degree angle, when you bisect it, you get 45 degrees. If you have 60-degree angle, when you bisect it, you have two 30-degree angles. So in other words, you think about a pizza slice. Now you must share it, lay your sister, then you cut it in half. You introduce a bisector to it. So then our pizza slice will have two equal pizza slices. You see? So our pizza slice bisector, then two slices. Right. Make next slide. Okay, then you can carry on with the discussion there. What does it say? Using construction
to investigate the minimum conditions for triangles to be congruent.
All right. We're going to discuss congruency. Do you know what congruency means? Congruency. Okay. Take out your left hand. After finishing writing, take out your left hand and put it up. Take your right hand. Now put them together like this. Okay. You can see the one hand fits exactly the same on the other hand, or more or less exactly the same. Right. So when we have two triangles, this is triangle A. Let's call it A, B, C. We have triangle A, B, C. And we've got triangle D, E, F. D, E, F. What congruency means, so congruency, what it means, it means if you take triangle ABC and you put it on top of triangle DEF, or you take triangle DEF and you put it on top of triangle ABC, they will be exactly the same size. You won't be able to see one katukorayo, or one will not be smaller. That's what congruency means. So triangle ABC fits exactly on top of triangle DEF and vice versa. Now in grade 9 you use construction techniques to prove that congruence. So we can try and explore how to do those. So when triangles are, you read that part?
When triangles are congruent, all three angles and sides of both triangles will be equal. We use the symbol 3 lines to show congruence. So if triangle ABC is congruent to triangle DEF, we write triangle ABC is congruent to triangle DEF.
100%. And I like that you read the 3 lines as congruent. So that's how you read it even when you've proven it in grade, I think 10, 11, and 12, you will use the congruency ways of proving congruency, and you'll always conclude by quoting that if you have proven that the triangles are congruent. Right, now carry on.
This means that the corresponding angles of the two triangles are the same size. So angle A is equals to angle D, B is equals to angle E, and C is equals to angle F. The corresponding sides of both triangles are also equal. So AB is equals to DF, BC is equals to EF, and AC is equals to DF.
Yes, so in other words, this side will equal that side, this one that side, this one that side, and this angle that one, this angle that one, and this angle that one. They'll all be equal. Just like your hands when they are on top of each other like this. Okay? Alright, and then the next part.
Complete this investigation and record your results to work out which minimum conditions are necessary for two triangles to be congruent to each other. Remember to use what you have learned about constructing triangles.
Oh, okay. So we didn't do the part of constructing triangles, ne? I would like to trust you to do that on your own. So practice that so that you can understand it. But we are going to discuss the minimum conditions for congruence. And I believe the minimum conditions for congruency are you must have all 3 sides equal. Next slide. Ne? Condition 1, it's side, side, and side. Ne? So all 3 sides must be equal for congruency. The second one is, I believe, side, angle, side, meaning 2 sides and the angle between the 2 sides. Must be equal for congruency. So let me just quickly check. Congruency conditions. Yeah. Yes. Then the next condition, 2 angles and a side must be equal. So in other words, a side, the angle opposite the side, and one angle next to the side, ne? Must be equal for congruency. Then we also have angle, side angle, which means an angle a side next to the angle and a different angle next to the side must be equal for congruency. And lastly, we have right angle, hypotenuse, and side. So one pair of angles, one angle must be 90 degrees. The side opposite the angle must be a hypotenuse, and lastly, a side must be equal between two triangles for congruency. Ne? Yeah, so those are the conditions for congruence. So you must have three sides equal, a side, an angle and a side, that angle being between the sides, two angles, and a side opposite that angle, as well as two angles sandwiching a side, and then lastly, the right angle, a hypotenuse, and another side. Ne? So far, is everything making sense? Okay, are you enjoying yourself? Alright. When you're done, you can click next slide. Alright, then we're gonna do geometric shapes, quadrilaterals. Alright, so we're going to revisit some definitions, ne? Triangle equals three angle, ne? Three angled shape. Okay. Now we have another shape that we're introducing, which is quadrilateral, ne? Quadrilateral. Now quadrilateral means four-sided shape. Four-sided shape, ne? Because the quadri means four and the lateral means side, ne? So just as tri means three and angle means angle. So that's how they formulated the words. So eventually we'll have and here we will have side 1, 2, 3, and 4. Side 1, 2, 3, and 4. That one. So that's how these we can. So lateral means side. Yeah, lateral means side. So if you are able to think laterally, it means you're able to think sideways. You can think in terms of connecting between other people and things. Then there's vertical, which means up and down. But Those are other words for another time. Now, you can make next slide there. All right. So when we construct quadrilaterals, like with the triangle, do the exercises of constructing the quadrilateral. I agree you've got compass and pencil and everything. So you follow these instructions. That will be your practice and your homework. When you follow them and you do them, you will understand them better than Mr. P is explaining them to you. Yeah, when you do them yourself, you'll understand them better. But there are different types of quadrilaterals. So we'll discuss them there. Ne? So types of quadrilaterals. Ne? We've got square. Square is a four-sided figure and all the sides are equal. Ne? So what are the properties there? Oh, no, never mind. Yeah. And then we've got what other? What's this? Rectangle, ne? Rectangle. If you take two right-angled triangles and that have like two sides equal, you get a square, right? And if you take two right-angled triangles where the one side is longer than the other, and I'm saying side, fully noting where the other side is a hypotenuse. So because it's right angle, we don't really talk about it. We just talk about the differences between these two sides. Ne? So the long side will be equal to the other long side. Ne? So rectangle is like two right-angled triangles where the one side is longer. So if you think about your fingers like that, that's a right-angled triangle. Now when you join them, you have a rectangle. But if it's a square and the other side equals the other side, then it makes a nice shape like that. And then what's the other quadrilateral? Parallelogram. Alright, that one, parallelogram. Remember what we talked about parallel lines? Did we talk about parallel lines? Or they go in the same direction but they never cross? We didn't talk about that. Okay. So parallel lines are lines that will run from wherever they start to wherever they end. They will run in the same direction, but they will never touch or intersect. Because if they intersect or converge, then they're no longer parallel lines. So this here is parallel. This here is not parallel. Ne? So from parallelogram, we have two sides that are parallel and equal, and we also have another pair of sides that are parallel and equal, but not equal to the first two that are parallel. And a parallelogram will have diagonals like that. You know that fun diagram, ne? Do you know it? Where you have corresponding angles, co-interior angles, and alternate angles. Remember that. Parallelogram is a great place to identify co-interior and alternate angles, because now when we have these two lines parallel, then these angles become equal. Like that shape, the N in the fun diagram, ne? So I'll just draw fun up there so we can remind ourselves of it. Ooh. Again, these will be red. These will be green and yellow, and corresponding would be blue. So we might not deal with corresponding angles, but at least we've got alternate angles. See, like in fun there where they're red, we'll have alternate angles. So the same, we'll also have another end there where these two angles are equal. You see? And we'll also have these angles equal because there's a Z there or an N shape. See, alternate angles. And we will also have another shape like that which runs like this, making these angles, let me just give them 4 arcs, 3, 4, 1, 2, 3, 4, and those would be equal. You see? Again, the angles inside a quadrilateral, when you add them, they add up to 360 degrees. When you have a square, you have 190-degree angle there, plus this one. Co-interior angles give 180. So you have 90, 180. Now the shape is closed, unlike here. So now you have plus another 190, which is 270, plus another 90, which is 360. So that's 1, 2, 3, 4 90-degree angles give you 360. Same as a rectangle, right? Now, for parallelogram, it's also the same. So this angle plus this angle should give you 180 degrees. And also, I think we will prove this at some point, but this angle equal the opposite angle to it, as well as this angle here will equal the angle opposite to it. So that when we look at them, we have this case here of co-interior angles. This case is there, this case is there, and this case is also when you look at it like that. So whether you look at it from this direction, that direction, that direction, or that direction, you still get that thing. And if for some reason, maybe you had lines going this way, then you would have corresponding angles. So this one would equal that one. You see? Yeah. That one would equal that one, etc. And again, these would be alternate angles, so this one would equal that angle as well. So it doesn't have to necessarily look like an N. The lines are still parallel. Then there is a line that runs between them. So even though they don't necessarily make an N, they still make a Z shape. The angles might not be sharp, but they're equal because they follow this pattern. Do you have questions so far? No questions. Okay. Then we have another shape there. What is the name of the shape after parallelogram? Rhombus. Okay. Rhombus. So rhombus is a parallelogram, but a special parallelogram. Right? It's a special parallelogram because it's kind of parallelogram but like square, you know, whereas parallelogram is like rectangle. Ne? Yeah, so these sides will be equal, just like square will have all 4 sides equal. And I think the diagonals intersect each other at 90 degrees, if I'm not mistaken. Whereas with a normal parallelogram, the diagonals do cut each other up, but only those two will equal, and only these two will equal. Whereas with a rhombus, here will equal and there will equal. Yeah. And then the same things that happen with the parallelogram regarding the angles is the same. Ne? Yeah, so the angles dilekana hoswana in the rhombus as with the parallelogram, but just the sides are more equal. And then we have another quadrilateral. What is it called?
A kite.
Kite. Salwa, you build a kite. Then you flew it. Okay, how high did it go? I'm not sure.
You need to get.
It must have flown very high. We're gonna build one this year. The windy season is about to start. Not you're too big for a kite. What do you play now? Call of Duty. You play Call of Duty? Is it? What level ma?
16.
Level 16. So it's not long since you played.
And we PlayStation last week.
Oh, so you're playing it on PlayStation. Okay. I'm on mobile. I play it here on my tablet. We must play together sometime. Okay, so kite would look like this, ne? It will have two adjacent sides equal and the other two adjacent sides equal. Then the diagonals, they would cut each other at 90 degrees. But these two will equal, those two will equal, these three will equal, but these other two diagonals are not equal. Then these angles will be the same measurement, and these two will also be the same measurement, but these might not necessarily be the same measurement. Ne? Yeah, so, and then is there another quadrilateral after that? No, okay. Then we can move to the next part of the discussion. Let me see. On the next page, what do we have? Okay, again, so in your book, from page 111, they show you different sizes of these quadrilaterals. Draw them yourself, and then I'll feature you so that you can, as you interact, there's a benefit to doing things with your hands. You see, when you play Call of Duty, you get better at it because you keep playing. With maths is the same. You get better at understanding the game of maths as you interact your hands and eyes at the same time with the game of maths. It's a bit boring than Call of Duty, Mara. It works the same. The more you do it, the more you get better. Alright? So, yeah, do these, get your homework as well. For your self-study, not homework, self-study. Because I'm sure they give you homework, but you need to study by yourself. Okay. Different types of triangles. Let's discuss these ones. What's the first triangle?
Acute angle triangle.
Okay. Acute angled triangle. Alright, so it's got all three angles sharp, ne? All three angles are less than 90 degrees. Ne? Then the second type of triangle?
Obtuse angled triangle.
Obtuse angled triangle. Okay, remember the obtuse angle is that one that has more than 90 degrees. Obtuse angled triangle. So one of the angles is larger than 90 degrees. Ne? So one angle larger than 90 degrees. And then the third triangle?
Right angled triangle.
Right angled triangle. Okay. So one angle So right angled triangle. So one angle equals 90 degree. And the fourth type of triangle?
Equilateral triangle.
Equilateral triangle. Lateral triangle. This is important because an acute angled triangle will have angles that are less than 90 degree, but only when each of the angles equals 60 degrees. Then it's an equilateral triangle because all the angles are equal, meaning all the sides will be equal. So this is an acute angled triangle. That's an equilateral triangle. So acute angled triangle with all angles equaling 60 degrees. So 60, 60, 60. And this triangle also becomes important for trigonometry. But you'll get to that when you get to start trigonometry. I'm not sure if you do it in grade 9, but we'll talk about it. And then the other triangle?
Isosceles triangle.
Isosceles triangle. Remember we talked about a triangle where the two sides are equal in length and then the two base angles are equal, but the other angle has a different size. Yeah, so that's that isosceles triangle. It's also likely, and it can be an acute angled triangle or an obtuse angled triangle. So this one is an acute angled form. So maybe this one is alpha, that's beta, and ABC, then AB equals BC, angle BAC equals angle BCA. And it can also look like this, where you have an obtuse so A, B, C. You see? The acute angle version and the obtuse. Alright. Yeah. So then you can do the next slide. Alright. And the next okay, let's just read through. Oh yeah, what's the other one?
Scalene triangle.
Scalene triangle. Okay. And that would be 5, 6. Okay. 6. Scalene triangle. What are the properties of a scalene triangle there when you read them?
It has no equal sides and has no equal angles.
Alright, so it can be like that. It can be like that. It can also be a right angled triangle. No, but for purposes of clarity, we can just make it general, where this side is not equal to that side is not equal to those sides, and the angles are also different. So no equal angles or sides. Can be sharp angled, can be acute or obtuse. Can be acute or obtuse. Or acute. Obtuse or acute, yeah. Then read for us the properties.
Properties of triangles. The sum of the interior angles of any triangle is 180 degrees.
Remember that experiment we did with pieces of paper. Alright, carry on.
You can show this by cutting a triangle out of paper as shown. Tear the triangles A, B, and C of the triangle. Tear the angles A, B, and C of the triangle. Fit the three angles along a straight line like a puzzle. The three angles of the triangle should fit together perfectly on a straight line. A straight line is a 180 angles. So this shows that the sum of the three angles of any triangle is 180 degrees.
It's exactly the process, yeah, the experiment we did. So we did it before we even got to it in the book. Yeah. So maybe we can skip that and look at this one, theorem of Pythagoras. I think that's also another important. And you must remember this theorem, ne? Because you're going to use it right up to matric and even beyond. If you decide to pursue studying math and science after matric, if you do math and science after this year. Ne? So Pythagorean theorem. So a little bit about Pythagoras, ne? Pythagoras was a Greek philosopher in ancient Greece, ne? Do you know what philosophy is? Philosophy is it's like thinking. But to our philosophers, people who are philosophers tend to think a lot, contemplate a lot about the world, things, etc. A lot of famous philosophers also happen to be, some famous philosophers happen to be mathematicians at some point or another. For example, Archimedes was a philosopher, also from ancient Greece, but he came up with what they call Archimedean screw. Do you know the Archimedean screw? Okay. It's a, you see how a screw looks, ne? In a lay, those things that go around like that. Like a screw looks like this. And then it has those things. Ne? So the Archimedean screw, you put it in a river, ne? Let's say so. You put it kamora, and then it's inside like a tube. Ne? Inside a tube. So what it does is when you turn it on top, it picks up the water and then it sucks it up into a different container. The person who came, it's called Archimedean screw. Archimedean screw. Because the person who made it was called Archimedes. Ne? So Pythagoras was one of those thinkers who came up with things like that. So he said, and then I don't know what he was doing when he came up with it. But one of the things was that he studied geometry in ancient Egypt, I believe, and other parts where you could study geometry. So Egypt was one of the places where you could go and gather knowledge of the maths and whatever at the time. So his theory, which is called Pythagorean theorem or theorem of Pythagoras, is named after him, just as that screw is named after Archimedes. Ne? So his theorem was that if you have a right-angled triangle, ne? Maybe let me draw it here. Ne? Make it a little bit smaller. Ne? So his theorem was that if you have a right angled triangle like this, ne? And you have this side called A, this side called B, and this side called C, then, and this is why shape square exists, ne? Square means you take the one length, and when you square it, you project it over an area where all the sides are equal, and that gives you a square where all the sides are equal, ne? So when you have the square of side C, ne? The square of side C. So in other words, the area you get when you project this way, it equals the sum of the squares of A and B. So the square of A plus the square of B equals the square of C. Now I'm going to draw it so that we can picture it. Ne? So if, let's say, this side, let's say C equals 5, A equals 4 and B equals 3. Ne? Then what we will have A is 4 and B is 3. Okay. Then what we will have, ne? If C is 5, we will have 1, 2, no, that's too close. 1, 2, 3, 4, giving us 1, 2, 3, 4, 5. All right, that works out. Nah. Then A would be 1, 2, 3. That gives us 1, 2, 3, 4. Also perfect. And then B would give us 1, 2, which gives us 1, 2, 3. Yeah? So we're going to square this distance of 5 units. So to square it would be 5 times 5, isn't it? It would be 5 to the power 2, which is 5 times 5. Which is how much? 25. All right. So we're going to have 25 blocks. And this you can do with little tiles. So we're just going to make that. So we'll have block number 1, 1 square, 2 square, 3 square, 4 square, 5 square. So this goes all the way until it makes a square. 1. So that'll be 2, 3, 4, then 5. Ne? So when we add up these squares, they must give us the sum of the other 2 squares. So we're going to do the square of side A. So since it's 4, it means we'll have something that looks like this. Ne? 1, 2, 3, 4. So it must go all the way until it gives us that. Ne? And that means also we do the same for B. So it should be by 3. Yeah. Ne? So in other words, the square of A has got 16 blocks, isn't it? The square of B has got 9 blocks, isn't it? And again, we said the other one has got 25 blocks. So that means if we take 25, it must equal 16 plus 9. Ne? And if you do that calculator, you will see that it is true. Isn't it? Yeah, because if we take 16 and we add 9, we get 25. Now one. So this is Pythagorean theorem. We will use this theorem in geometry, in trigonometry as well. Yeah. So in trigonometry, because trigonometry is triangle measurement of triangles. Yeah. But this is more or less what that means. Yeah. Pythagoras theorem. Next slide. Just read for us. It's the same thing. Oh, okay.
16 is equals to 25.
Oh, okay. Then the other thing, if we want to work out the length of C, C will equal the square root of A squared plus B squared. But that also means we can solve for A or B. So let's say we don't know A, but we know B and C. Then A squared will equal C squared minus B squared. Can you see how we came to that conclusion? Why? How did we come to that conclusion?
Because we don't have A.
A.
We moved A here and moved C squared here.
Okay.
And it made the plus sign convert into the minus sign.
Okay. Now those are called additive inverses. It's correct that you identified like that, So we took the additive inverse of b and we added it to both sides. So then we'll have c squared minus b squared equals a squared plus b squared minus c squared. The b squareds remove each other, so we're only left with a squared. Then we have, so we're only left with a squared, and then we have it equals c squared minus b squared. Then that means we will solve for a by taking the square root on both sides. So a will equal c squared minus b squared square root of. And in the same way, b squared will equal c squared minus a squared, and b will equal the square root of c squared minus a squared. Okay? All right. All right. Yes, so we can do next page. All right. Then, okay, so refer to Pythagoras, ne? And then what is there at the bottom?
Establishing the minimum conditions for congruent triangles investigation.
Okay, we discussed congruency and we discussed the conditions. So we can pass that chapter. Ne? Do you want us to do an example? Yeah? Are you sure? So you can do these examples if you're okay. You're confident you can do them. All right. All right. So after congruency, ne, we come across what is called similar conditions. Now, like we discussed, congruency, ne, we can also discuss similar triangles. Similar triangles. So similar triangles, you can have a triangle that will be this size, ne? And then you'll have a triangle that will fit inside it, but maybe it is a smaller size of the same triangle. For an example, if this, let's say that's A, B, C, D, E, ne? Then triangle A, B, C would be similar to triangle D, E, C, ne? So in other words, they have the same shape, but not necessarily the same size, ne? Same shape but not same size. Congruency ki same shape, same size, ne? Similarity ki same shape but not same size. Yeah. So we're going to look at the conditions. It's theorems rather. Okay. So we're going to look at how to test for similarity. Yeah. Ne? Before we test, if we take the ratio of DC to AC, it must equal the ratio of EC to BC, and it must equal the ratio of DE to AB. Ne? Yeah, in other words, and if we look at it with triangles that are like this, and this is A, B, C, and this one is maybe a smaller size of that one, ne? And this is P, Q, R, ne? Then A over P must equal B over Q must equal C over R, ne? So that's this condition, and that's also that condition, ne? Then to test for similarity, two corresponding angles, that's the first condition. Two corresponding angles must be equal. So what does that mean? This angle and that angle are equal. And one of this looks like the Venn diagram, corresponding angles, ne? So again, Venn. So let me just put Venn there. So again, that drawing, and now we've got corresponding angles. Let's see. So this one will correspond with this one, whereas that will correspond with that one. So that's the first test. Then the second test, if three corresponding sides are in the same ratio, three corresponding sides remember, ratio is just a way of saying a fraction, ne? And it's like when you're mixing wild island, you mix 1 cup wild island to 7 cups water, or 1 cup oros to 3 cups water to get the correct flavor. That's what the packaging recommends, ne? So it's a ratio, just as these ones are ratios. That one. And then also, the ratio of two pairs of corresponding sides are equal, and the included angles are equal. So ratio of two pairs of corresponding sides equal, and included angles, ne? Are equal. So that's how we test for similarity. Right. But for this one, we must know the angles. For the first condition, we must know the angles. Here we must know sides, and here we must know also the sides and the angle. Sorry, King, this we must know the two sides and angle. All right. Next slide. Okay. So you think you can do self-study to rehearse these concepts because I think in the next page you have to prove similarity, isn't it? Yeah. So here's the nice thing about similarity and congruence. You're gonna do them all the way until matric. But you know the nice thing in matric, ne? You easily get asked to prove similarity between two triangles, and just by knowing the angles you get a lot of marks. So it's important to keep this concept in your mind, even next year and the year after and in matric. But that's if you decide to study maths going forward. Ne? I think this is also similarity. What's this here?
Solving geometric problems.
Geometric problems, okay. You think we should do one problem? Would you like to do one problem to see if we've learned anything? Two. Okay. And then okay, I just want to see the next page here. Oh, okay. Yeah, so we'll do 2 problems for triangles, discuss a little bit about quadrilaterals, and then 2 problems with quadrilaterals. Yeah. All right, so let's solve this one here, where we apply theorem of Pythagoras. Ne? So what do we have? The length of a swimming pool is 15 meters and the width is 8 meters. Ne? So we've got a swimming pool. The long side is 15 meters and the wide side is 8 meters long. Ne? Alright, so we must calculate the length from one corner to the length in the opposite corner. Ne? Alright, so I'll just draw maybe one person swimming in there. I don't even know how to draw. Okay, so just make them look like they're underwater like that. Yeah, okay. So we must find out how long it is. Let's call these points A, B, C, and D. How long it is from A to C, ne? So if this guy was to swim all the way this way, in that direction, how far you do have to swim, ne? So we can use Pythagoras. So we can use Pythagoras. That means AC squared will equal AD squared plus DC squared. So we know AD, it is 15, we have to square it. And we know DC, it is 8, so we have to square it. And 15 times 15 is 225, and then 8
64
times 8 is 64. Well done for spotting that without a calculator. Then we must add 225 to 64 and we get 289, but that is AC squared, okay? Therefore AC will equal, the square root of 289 is 70. So that means if we do that thing at the blocks, we will have 17 by 17. This will be 15 by 15. This will be 8 by 8. Yeah. And the next example.
A gate has the following designs on it. Calculate the magnitude of the angle marked X.
Okay. Let me quickly copy it. Because you're going to look at the book now. So our gate sorry. Gate example. Yes, do the thing. So our gate looks like this. Alright, and then it's got 18 centimeters at the top. And then okay. So maybe here's the center. We know that this height is 18. We know that that height is 18, but the hypotenuse we don't really know. Get design now on almost. And it's like this. Alright. So we're told that this angle is 27 degrees. So this would be A, B, C, D, E. Nah? Alright, so that's 90 degrees there. That's also 90 degrees there. Alright, so we must find the magnitude of the angle marked X. Nah? Alright, thank you. Thank you for allowing me to copy from your book. So, we must find the magnitude of the angle named X. Correct? Firstly, we need to think about geometry. We know that AB and DE are parallel because they're vertical, and these are right-angled triangles. So what does that tell us? It means, since it's a gate and there's, so let's say BC equals CE. And this angle also equals 27 degrees. Nah? Then what that means is we will say the angle at E is 90 degrees because it's a right angle there. So that would be angle DEC. Then the angle at C, which would be DCE, is 27 degrees. Then the angle at D, which is EDC or CDE, is X. But we know that the sum of angles in a triangle is how much? 180 degrees. So that means DEC plus DCE plus EDC must equal 180 degrees, and that's the sum of angles in a triangle. Ne? So now we substitute. How much is DEC?
90 degrees.
100%. And how much is DCE?
27 degrees.
All right, well done. And how much is EDC?
X.
It's X with the unknown. Yes. Then they all equal 180 degrees. So now we must calculate. So if we take additive inverses, 180 degrees minus 90 minus 27, 90 minus 27, that would be 63. Yeah? Okay, so we've done our 2 examples on triangles. Now we can quickly look at quadrilaterals, do 1 or 2 examples, and then we call it a day. Yeah? All right, so we can quickly look at we're here, ne? We Okay, we've talked about the different types of quadrilaterals, so we won't repeat that. But just quickly read the properties so we can see what we skipped.
Properties of quadrilaterals. The interior angles of any quadrilateral add up to 360 degrees.
Well, we talked about that, ne? All right.
You can show this by cutting a quadrilateral out of paper as shown. Tear the angles A, B, C, and D of the quadrilateral. Fit the four angles together like a puzzle.
Just like with the triangles, yeah.
The angles of a quadrilateral should fit perfectly together around one point to make a revolution
of 360 degrees, yes.
A full revolution is a 360 degree angle. So this shows that the sum of the four angles of any quadrilateral is 360
degrees. Alright, so we didn't really miss anything there, ne? Okay, so these you can study on your own. This is constructing a quadrilateral. This is geometry of straight lines. Okay, let's do geometry of straight lines, and then we'll do I think geometry of straight lines in a level quadrilateral. So we'll just carry on from here. Ne? Alright, so read for us this part here.
The intersections between straight lines produce special angles. The relationship between angles formed by these intersections can be used to solve problems.
Okay.
Angle relationships and properties.
Alright.
Two adjacent angles that are supplementary add up to 180 degrees.
Alright, hold there. Supplementary. Do you know what a supplement is? Our class, this is a supplementary class. I get to attend a school. That's your main class. So we supplement that class with your tutoring class. That's supplementation, is to add. So when they say angles that are adjacent are supplementary, add up to 180 degrees, it means when we have a straight line and we've got an angle A, then this angle here becomes B. Right? So now you understand supplementary from an application that you are experiencing. You see? That's nice, isn't it? Alright, cool. Then the next part.
This is because the angle of a straight line is 180 degrees.
Good. Alright, so we've proven that with the triangle exercise. We've shown that rather. And now we can safely say that even if it's two angles or four, but as long as they're on a straight line, they give us 180 degrees. Alright. Then the next one.
When two straight lines intersect, the vertically opposite angles are equal.
Okay. So when we have a line and we have another line intersecting, ne? So we will have an angle there and we'll also have a different angle there, ne? What happens is, remember the lines this way, the angles this way add up to 180 degrees. That means the angles this way must also add up to 180 degrees. Now what also happens is that what we have going on up here is the same but in the opposite direction. Ne? So what that creates is a situation where this angle becomes vertically opposite that angle. And this angle becomes vertically opposite that angle. So we call these angles vertically opposite. So if we have that as alpha, and that's beta, that's also beta, and that's alpha, we call them vertically opposite angles. So alpha will equal alpha because they are vertically opposite. So that's what that describes. All right. Then carry on.
The angles around a point add up to 360 degrees.
All right. Angles around a point. So that means in this case, where they are vertically opposite, if we add them, so we'll have alpha plus beta plus alpha plus beta should equal 360 degrees. Then 2 alpha plus 2 beta will equal 360 degrees. So if we take out a common factor, factorize of 2, then we have alpha and beta will equal 180 degrees, which still kind of takes us back to there. Yeah, but it's a lot easier to understand this one of 360 degrees if we have, let's say we've got another angle there, and then the other angle is like that. So if we have A, B, C, and D, then A plus B plus C plus D will equal 360 degrees. Yeah. All right. Then, okay, read the next part.
A line intersecting another line at a right angle or 90 degrees is said to be perpendicular to that line.
All right. Make the next slide. So if we have a line and another line intersected at 90 degrees, and this is important on so many applications for geometry from grade 9 onwards, because even in circles, this becomes a very important thing to know. But anyway, we'll call this a perpendicular line, which is that one there. So that's alpha, beta, gamma, and theta. So this one will be perpendicular line. Okay, carry on.
We use the symbol.
It's like this, It's like an upside down T. Yeah, that's the symbol for perpendicular. Yeah, so we use the symbol.
We use the symbol perpendicular to indicate perpendicular lines.
Okay, that's very good. And the next part?
So when a horizontal line intersects with a vertical line, the angle between them is 90 degrees or a right angle.
Yes, so the line that is straight is horizontal. You know where that word comes from? Horizontal. So when the sun rises, in the morning, when the sun rises in the morning, or it sets in the evening, that line is called a horizon, right? So every line that is like that is called horizontal. Now, vertical is to go up and down. So in physics in grade 12, if you decide to study maths and science past grade 9, in grade 12 there is a chapter called one-dimensional movement in the vertical direction. What that means is things that move up and down. So vertical means up and down direction. Horizontal sideways direction. Ne? So perpendicular will have a vertical intersecting a horizontal. Ne? And they form 90 degrees. That's what that means. Okay. Next.
Two adjacent angles that are complementary and up to 90 degrees.
Okay. And next slide. So angles that are complementary. To complement means to be the other half or the other part that's missing in the other. Ne? So if we have a perpendicular angle and one of them equals 30 degrees, then its complement is 60 degrees. So again, if we have a perpendicular situation, that is alpha, that is beta, then alpha plus beta would be 90 degrees, which would make them complementary. Ne? All right. And read the next part.
Angles A and B are complementary. Parallel lines are lines that never meet. They are always the same distance apart.
Okay.
Arrowheads are used to show the lines that are parallel. We use the symbol
Is it like an 11? Okay. So remember we have congruency, we have similarity. Now this means parallel. Ne? Congruent, similar, this is parallel. Ne? So those lines, it looks like let's say you have two lines there where you're writing. Instead of writing 11, you'll just do two lines and they look like they go below the line like that. You see? So this is how we indicate parallel. Ne? And so that's how we indicate parallel. Then on the lines themselves, the arrowheads indicate parallel. You see? Yeah, so when you are writing, you just, on your lines like this, you'll just make parallel like that. But on the lines, you do arrowheads. Alright, now if you have two parallel lines like this and then another line intersects both of them, that line is called a transverse line, I believe. Yes, transversal line. So that means we've read this part. And then again, from here, you can look for that game. It's not exactly fun because it's maths and it's not Call of Duty, but we'll pretend it's fun so that we pass again. We'll pretend it's fun so that we pass. Ne? So here, when you have two parallel lines and a transversal, always think of fun. Yeah. So again, corresponding angles will show up there, which would be these ones. So let's just write corresponding, co-interior, which are also supplementary, and alternate. Yeah. All right. Then let's do two examples and then we call it a day. We've got 12 minutes left before my next class starts. Ne? So we'll do okay. Let's do this one. Ne? We have here 106 degrees and here 106 degrees, ne? This is line AB, this is line CD, ne? We are not told whether or not they're parallel. Instead, we are given the angles and we are asked to prove that AB is parallel to CD. How will we prove that?
Using congruency.
Congruency is for triangles, so we don't have triangles here. Remember fun? So if we have alternate angles, co-interior angles, or corresponding angles, and they meet the conditions that make them corresponding co-interior alternate, then it means the lines will be parallel. Parallel lines give us the equal angles like that, or the co-interior angles like that. But if the angles meet the criteria of being alternate, co-interior, or supplementary, then the lines must be parallel. So the same way you say that if the lines are parallel, the angles will be equal. You can say if the angles are equal and the lines look like that, then the lines must be parallel. So what we can say here is that the angle on AB, that is 106. So let's call these points D, sorry, maybe not D, but E, F, and then this one will be G, that will be H, ne? So now we can say angle AEF equals 106 degrees, and it's given. So we have a statement, ne? Okay. We state that AEF equals 106 degrees, and the reason is that it's given. I get it's given. And also angle DF E equals 106 degrees, and it's also given, ne? That means angle DFE will equal angle AEF, and this means that line AB will be parallel to line CD because we've proven that angle DFE equals angle AEF, and they are alternate angles. So that's how we can prove that lines are parallel, because we're given angles that are equal and alternate. Alright. So these angles are alternate, and we've proven that they're equal. Alright. So don't make it difficult. The same way when you can say, if I see two parallel lines, then the angles alternate must be equal. If I'm given angles and they are alternate, then it means the lines must be parallel. Yeah. So let's do another example. Got a trapezium. So that will be P, Q, R, T, S. Then from P to T we have a diagonal. Above we've got A, up here we've got 22 degrees. Here we've got R, we've got B, we've got C. And here we've got 80 degrees. Here we've got 58, ne? And this is D. And we're told that these lines are parallel. Okay, so find unknown angles. Ne? So we must find unknown angles. Where would we start? We must have statement. Ne? Every time when we answer geometry questions, it's always best. I won't say this is the only way. I mean, if you can find a way to present your answers well, that's up to you. But this often gets you a clear way of thinking about. For me, it gives me a clear way of thinking about these problems. So now I'll start with this angle because it's the easiest. And it's easiest because it is an alternate angle. Can you see that? Ne? So I'll start by saying angle D equals 58 degrees, which equals angle PQT. That is because they are alternate angles, and they are alternate because the side PQ is parallel side RS. So when I mention which angles are equal because alternate, I must mention also the sides that are parallel. That way you get full marks. Yeah? That way you get full marks. Alright, so now I've found angle D. Now I'm going to attempt to find this angle here. How will I find it? I'm going to take the sum of angles in a triangle. So I will say angle A plus 80 degrees plus 58 degrees must equal 180 degrees. The reason is because triangle PQT and the sum of angles of a triangle equal 180 degrees. Ne? Alright. So when I solve and I make additive inverses, 180 minus 80, that's 100, minus 58, and that would be 42. So this would be 42 degrees. Ne? Now I'm left with angle C and B. So C, I can also equate to angle A because they're alternate angles. Can you see that? Because PQ and RT are equal. So angle A equals angle C, which equals 42 degrees. Alternate angles, and again PQ is parallel to RT or RS, it's fine. And then that gives me 42 degrees. Now I'm left with angle B, and angle B is an obtuse angle, so it should be larger than 90. So angle B plus 22 degrees plus 42 degrees, remember C is 42, that must all equal 180 degrees, and this is from triangle PRT, and the sum of angles of a triangle equal 180 degrees. Then that is B equals 180 minus 42 minus 22 degrees. My brain is a bit tired, so I'll use a calculator. 180 minus 42 minus 22. 116 degrees. So B is 16 degrees. Yeah? Yes, it is correct. All right. So I just went for the easiest one I could quickly identify, because if I'm in a test, I'll think of the one that I'll easily quickly get. That one. I don't think the order matters, but unless they say start with A, then you'll have to think about how will I start with A. That one. Yeah, so that concludes our class today. Do you have questions? No questions. You want to leave now? You want to chase her? But thanks for coming. Yeah, we'll end here. So just be on the lookout. This video is going to be uploaded tonight. You should get it tomorrow or later